Alright, so that was method number 1. Let's move on to method number 2, which is much easier than this in my opinion, which is by way of induction. So I hope all of you know how induction works. If not, I will run you all through a short brief. So induction involves 3 steps. In the first step, we do what's called the base case. It's called the base case. And in this case, you just prove it for the value which is just given in the question. And in this case, we're going to take it to be 1. The next step is the induction hypothesis. This is where you assume the statement to be true for some n equal to k, and then using the fact, now this is important, using this fact that it is true for k, we prove the statement for k plus 1, and this is how we complete our proof. Now why does this work? Well, okay, so in the base case, let's show it for n plus 1. And now, okay, sorry for that. Suppose it works for n equal to 1. That means it work. Let's say k is 1. So now, if we do all these steps correctly, then n equal to 1 implies that it will work for n equal to 2. Again, taking k as 2, it will also work for k plus 1. So it's gonna work for 3, and it's gonna work for 4, and so on. It's gonna work for all the natural numbers. So this is basically why induction works and how it is a brief outline. So now let's do it. Write down a result. Right. So this is something we have to prove right now. Okay. So let's take the base case, which is just n is equal to 1. Case. All right. I'm sorry, n equals to 0. I'm sorry, as the base case, and now this is just going to be the integral from 0 to infinity of e to the minus x dx. And this is just easy. You just take the antiderivative, which is this, plug in the values. Now take the minus out. E to the minus of infinity, well, that's just going to go smaller to 0. And we're going to just have minus 1. So that's just 1. And which is indeed 0 factorial. Remember, 0 factorial is 1. It's not 0. I mean, it's assigned the value 1. There are many good proofs of that. So yes, this is true for n equal to 1, and our base case step is done. Now let's form a hypothesis. Assume for some n equal to k, we have this to be true. Alright, so we say this. Right, now we have to prove this for k plus 1. Okay, now we're going to use integration by parts. So let's just write down what we have here. Okay, this is what we have to prove. Now I'm just going to integrate by parts. Now I'm going to choose my u as this and my dv as this. Alright, so I hope you'll remember this. Integral u dv equals uv minus integral v du. So now let's see. Let's do it. U is x to the k plus 1. So our du is just going to be, well, x to the k plus 1 is just k plus 1 times x to the k by the power rule dx. Okay. Now our dv is e to the minus x, and again we've just integrated this already. So our v is just going to be negative e to the x. Okay. Now over here, what we do next is just substitute it, and we do uv minus integral of v du. So uv is going to be evaluated at the bounds of integration. Just going to write it like that. Then at the end we subtract. Now integral v du, now there's a minus here, so they both become plus together. of VDU, okay, k 1 times x to the k times e to the minus x. Hope I've got this right. And now this is our integral. Okay, now let's put in the values. Now for the first one we get an indeterminate form, so we use L'Hopital rule and we keep on applying it again and again, which will lead us to a constant at the top and e to the x at the bottom. So if we put that in there, we get 1 over infinity minus 1 over infinity, which is just going to be 0. So at infinity this is just 0. You can also notice that because e to the x is going to grow faster than x to the k plus 1. You can compare the graphs and see that. Okay, so at infinity, this evaluation is going to be 0. Now we subtract. Add 0. Add 0, x to the k plus 1 is 0, 0, 2. Anything is 0 except 0. So 0 minus 0, and this just goes to 0. So the first part of our integral is just 0. Very nice, very convenient. Because as you will see right now, since k plus 1 is a constant, we can just put that aside and write it as this. Now this is what we got. Now look at this. Look at the part inside that is very familiar, because in our hypothesis, we just showed that this thing was k factorial. So therefore the whole thing should be equal to k plus 1 times k factorial. And by the definition of the factorial function, this is just k plus 1 factorial, and therefore we write that since it was true for k, 0, then it was true for k, and then k plus 1, we can write that this is true for all numbers, and here we are done. Or naturals, yes, we are done. So thank you all for watching this video. I hope you liked it. Please do share and subscribe to my channel. Thank you. This is Goranj Kapoor from The Maths Geek signing off.